we do. Everything is fine.
Okay, good. So probably it's time to 1 minute still.
Yeah, so 2 minutes. Let's say 2 minutes.
Okay, let's make it 2.
Can you make my second account co-host again? So I always leave because if I take 5 hours of video, then that doesn't like, my memory doesn't like it or something.
Yeah.
Thanks.
Okay, so didn't quite got what you say.
Yeah, it was for Ina, just about the recording.
Okay, I see.
All right, I think we can resume after the coffee break. So the 2 remaining talks of our conference, very good recording, I should also do that. And so the first one by Alexander Dolgov about primordial black holes and antistars. So please, the floor is yours.
Thank you. Okay, good afternoon, everybody except for Americans, for whom is good morning, I believe. Okay, so the title is here, and I want to start with a rather provocative statement that some predictions of our paper with Joe Silk in 1993 were recently proved by observation that they are correct. Namely, one thing was that we predicted mass spectrum of primordial black hole, which is extremely simple. It is log normal mass spectrum. And moreover, we predicted the value of m sub 0 together with Pasnov. And this mass is equal to horizon mass at QCD phase transition. So it is roughly speaking 10 solar masses. And another prediction is was really unbelievable, namely a prediction of antistars, about some amount of antimatter, some noticeable amount, small but noticeable amount of antimatter in our galaxy, in Milky Way. And it seems to be that there is indeed accumulation of the data in favor of this statement, that our galaxy contains some amount of anti-star, anti-nuclei, and whatever. So, and I want to stress that our paper was the first in the literature which used cosmological inflation and Affleck-Dine baryogenesis for the way to make, for means to make black holes. Well, later on, there are several, quite many works which use the same words, but completely different maybe mechanism, namely inflation and Affleck-Dine. Yeah, that was our, in fact, 2 papers. The first one was with Joe Silk and another with Masahiro Kawasaki and Nina Kevlishvili, which was some development of our ideas, and it even contained words cosmic antimatter and dark matter. In our first paper with Joe Silk, there was also mentioning in the title dark matter, baryonic dark matter. Baryonic means consisting of black holes which are really were made from baryons, mostly baryons or antibaryons. Okay, now let's go. First of all, I want to say that the predicted mass spectrum, log normal 1, is strongly confirmed by the data from LIGO distribution of chirp mass of LIGO distribution. It was analyzed in our paper with a big bunch of people in Sternberg Astronomical Institute in Russia, and we analyzed first publicly available but not really published data of LIGO, and then later on we used complete set of data, and you will see how well this log normal distribution describes the chirp mass distribution of the observed primordial black holes. And the best fit in our model was that M0 was 17 solar masses, not 10, but the result is only by order of magnitude, because it depends upon horizon mass at QCD phase transition, and it is not well-defined quantity, I think, within factor of 2. Okay, and as we try to compare distribution of observed by LIGO with astrophysical ones, we'll see that these are, at least naively taken, disagree with distribution, and one has to take several adjustments to get an agreement. Here is the chirp mass distribution. What is important, it is model distribution of relative number of black holes with certain mass smaller than m, and normalized to total number density. So it is not sensitive to their total number density. The parameter mu here in the mass distribution, this one is we cannot predict it, and if we would demand that all these black holes with the mass of 10 or 17 solar masses make all dark matter, we can normalize it, but otherwise we cannot say much from the existing data. It's noticeable, but it's hard to say how large is that. Some, I think, at the level of 10% is, at least for me, is a reasonable guess. Okay, so this is the data, and you will see you will see two fits, different ones, and with different parameters. You see that M0 equal to 17 perfectly well fits the data. And this is empirical distribution function, which is taken, blue ones, distribution function taken from the data. If we compare what we see for astrophysical models, then you can see that all astrophysical models do not, at least what we tried, do not well describe the situation. In fact, the case is slightly more complicated. There could be a mixture of astrophysical black holes and primordial black holes. And what we did, there was analysis. First is, sorry for interrupted myself. It is the analysis made later on when all data became available. It contains more data, but practically the result is practically the same as in the previous one. So LIGO data seems to very well confirmed log normal mass spectrum of predicted in this model. This is another one. It is related some kind of combined data with taken into account possibilities of astrophysical black holes, namely mixture, and well, anyhow, it's still strongly in support of log normal one. Now, another thing in favor of that black holes observed by LIGO are primordial, that first of all, they observed black hole with the mass of about 100 solar masses, and at least when they observed it, it was believed that such black holes cannot be formed. To this end, we need very massive progenitor stars, but in the process of collapse, it throws away all its matter, and black hole with 100 solar mass was strongly believed is impossible to form. And of course, after it was found, then there are some tricky models with internal heating or some other exotic by dark matter and some other more exotic possibilities were considered. So it's now not considered, not assumed that this is this creature is really impossible. But at least that time it was thought that such heavy black holes cannot be formed. But if they are primordial, there is no problem. 100 solar masses is sufficiently big. Black holes with 100 solar masses is sufficiently abundant in the universe. Then there is another thing that which was in a sense predicted in our paper with Pastnov, that in each globular cluster should be primordial black hole with mass about 1,000 solar masses, and the log normal spectrum thus supplies insufficient number of PBH to explain, to allow each global cluster to have its own central black holes. Our point of view was that globular clusters was seeded by primordial black holes, and they may be true for dwarfs. It is not, I would say, canonical belief, probably quite theoretical, but recent data, there was a paper, I forgot the authors, sorry for that, they claim that there are, at least where they were able to see, there are primordial black holes with so-called intermediate mass, about 1,000 solar masses, which lives in global clusters and maybe also in dwarf galaxies. There are some other things which are very interesting and makes problem from the point of view of normal astrophysical or whatever black holes, namely so-called supermassive black holes with masses from 100. It is a matter of terminology. It is maybe not necessary strict numbers. No, so-called intermediate mass black holes are considered to be in the mass range from 100 to 100,000 solar masses, and there are very many of those black holes. And also we have so-called supermassive black holes with masses from million and maximum, I think, 100 billion solar masses. And there are also too many. Supermassive black holes are supposed to be formed by accretion to the center, and with known accretion rate, at least with the standard, if you don't invent any amplification of the accretion, the universe age is short by, roughly speaking, more than by order of magnitude to create these monsters. And moreover, such supermassive black holes are discovered at very young universe, at redshift about 10, and it corresponds to the universe which approximately 20 times younger than our one. And to explain their creation, we need very massive seeds. And as one of the authors who observed supermassive galaxies said, it's so easy to make elephant, you only need to have baby elephant. But nobody knows how one can make baby elephants except for having very massive seeds. That seed should be of the order of 10,000, 10 to power 4, 10 to power 5 solar masses. In this case, one can make primordial supermassive black holes even in a very early universe. And in one of my talk, I even expressed point of view that practically all black holes in the universe are primordial. Maybe it's a little bit extreme. Okay, now I'll come to antimatter in the galaxy. As I mentioned, another consequences of our model with Joe Silk, there was that there should be a compact object consisting of antimatter. And what is now observed in the galaxy, that there is excessive number of positrons, too much. I will show that next slides everything. Now, anti-nuclei up to anti-helium-4 are observed. Then there are observations of excessive gamma rays, probably coming from a compact stars. And another thing which may be, it's not yet observed, but it is our suggestion how one can see anti-star, namely observation of X-rays with energies of about between 1 and 10 keV. And this is a project, in a sense, it's suggested to how to look. So there are a long story of observation of 0.511 line from galactic center, and it is evidently is annihilation of electrons and positrons at rest, and there are so many, unexpectedly many of those positrons living in the center. There are some other less intense line which is seen somewhere in the in periphery. There are several works, and there was much longer story. There was SP1 and SPI and integral, which make very accurate observation, and several other ones. So this is well-established thing, but the origin is maybe not clear. It was believed that there is some story more, I can skip it. It was believed that positrons are created in strong magnetic field of pulsars, but at a recent talk by Sam Ting of November 10 of last year, so he said that they measured very accurately and produced a diagram in the spectrum of antiprotons and positrons, and spectrum are precisely the same. So they by shape and by magnitude. And so since proton cannot be created by pulsar, and so Ting made the conclusion, so the same should be true for positrons, and there must be some other mechanism. An evident possibility, at least for me, because probably my point of view is a little sided to this antimatter stuff, is that there is a lot of normal antimatter in the galaxy. And another possibility is that positrons can be produced by antiprotons should be produced by some decays of dark matter, but it needs quite strong adjustment and unnatural. Here I should write antiprotons, but both is true. Protons cannot also be created by pulsars. Maybe they can, because there are plenty of protons around. Okay, and then another thing which is quite striking, that anti-nuclei was observed. There are several pieces of data by alpha magnetic spectrometer, or sometimes they call it antimatter spectrometer. Many in 2018 there are only how many? 8 events, 6 of anti-helium-3 and 2 of anti-helium-4, and they were reported at several meetings, but never published, only in this at colloquium and meeting and collaboration. And anyhow, secondary production of anti-helium-3 is practically impossible. Secondary production of anti-nuclei was studied in Duperrey et al. In 2005, and the predicted flux of antideuterium was 5 times smaller than the observed flux of antiproton. They could be produced in proton-antiproton collisions and antiproton helium collision, and it is very difficult to create antinuclei because you have to produce 4 antibaryons in a very small piece of phase space. So they have very small relative momentum. That's why they are their production is so strongly suppressed, and anti-helium is at least 8 orders of magnitude less efficient than production of antideuterium. And recent results, which is reported at this colloquium by think that the fraction of anti-helium to helium was even larger, that it is an attitude is 10 to minus 9. It is too much if one expect their secondary production. And he said that, I mean, same thing, that maybe they come from decay of dark matter or annihilation of dark matter. Anyhow, he also expressed crazy hope, sorry for saying that, even anti-silicon may be observed in their detector. But in this case, one should surely say that it is real antimatter living in the galaxy. Well, but maybe that the flux of anti-helium is even much higher than the observed one, because IMS is sensitive to very energetic anti-nuclei, but if we have real antimatter, there could be much more lower energy anti-helium, and they most probably would escape registration in alpha magnetic spectrometer. And I repeat that the suggestion by Samuel Tink that this anti-helium-4 appeared as a result of dark matter annihilation. It was immediately invented. Theorists are clever guys, and they immediately invented some mechanism to explain it without invoking antimatter. This is simply another review which of production of anti-nuclei in cosmic rays, but there is not much different with respect to the old one. Okay, now it was a result of last year, namely statement of a possible existence of antistars in the galaxy. This is a paper by 3 astronomers, and Deporqueux, Thibaldeau, and Peter von Bolmus, whom I met recently at a conference at Carges. And he's quite cautious about saying that they discover antistars, but indeed there was about 14 objects which emits excessive gamma ray radiations with the energy of a few hundred MeV. It was quite not very good angular resolution, but at least at some places there were several objects which could be responsible for that. This is the picture, and I am able to find only 13 so-called antistars, but they say that there are 14, maybe there are 2 coinciding. This distribution over all the sky. So it is indeed tempting, but I repeat Peter's point of view that he said that it was not a proof. It was at least some hints. And this is the spectrum of gamma ray spectrum for hadronic annihilation of proton anti-hydrogen. And this is more or less in agreement with what they see, though it was calculation of our group. And the authors of this paper was very much interested in this spectrum. Now, there is another, I think, interesting idea that was published recently. And you see the author Bonder, Blinnikov, Bykov, myself, and Pasnov. All my co-authors are famous and very good Russian astrophysicists, except for Bonder, who is a very good person in particle physics and in detector. Okay, but it was the idea that proton does not annihilate with antiproton, not as head-on collision. They preliminary make atomic-like state like positronium, so it will be a kind of protonium, either proton antiproton or helium antiproton or vice versa, anti-helium proton, something like that. There is an excited state, and atom jump from one level to another down to direct collision with proton, which emits hundreds of mega electron volt. But in this case, we have very well defined lines with the energy of around several keV, from roughly speaking 2 keV, from the system of depending upon the level. If up to 10 keV, 11 if you want, 13, there's another level which could be about 25%, which may be really interesting case. Unfortunately, there are some problems with Rosita. Well, political ones, as I understand. Well, it's clear it's a really difficult situation, but it would be a good chance with Rosita to observe this narrow antiproton lines of proton antiproton atoms. In fact,
just
bound.
So you have 5 more minutes.
Oh, I see. I will be fast. There are some bounds of studied in our early works with Kozma-Bambi, Blinnikov, and Pasnov, which we found that fraction of antistars is allowed, and simply because annihilation proceeds in narrow level of antistars interacting with the gas. So there are plenty of space allowed. I skip this thing how one can see antistars different ways, but it is not especially promising. Next, there are some limits about normal anti-galaxy, which consists only of antimatter, and our galaxy. This is not very interesting for us, but there is a review by the same Fitter von Bolmus, who said that there are not more than 10 to minus 4 antistars inside 100 parsecs from the sun. It also doesn't contradict the existing data. Okay, let's go a few words about the model. The model is, as I said, Affleck-Dine scenario, which allows formation of very big baryonic number of order of unity instead of 10 to minus 9, and which is based on supersymmetric generalization, supersymmetric model at high energies. And there are some flat directions where Affleck-Dine field baryonic scalar could reach very big value. So it travels along these big directions during certain time, and then when it returned back, it started to rotate around origin, producing big baryonic number. What we did, we slightly modified this classical scenario, introduced coupling of Affleck-Dine scalar to inflaton. The phi is inflaton, and phi 1 is a certain value which inflaton passed during inflation. There is only fine-tuning in the model. Otherwise, it's general renormalizable interaction of two scalar fields. What happens when phi is close to phi 1? Chi goes far away. It evolves in accordance with Starobinsky diffusion scenario, and then phi passes object. Chi returned back to the origin and started to rotate on the way because of two type of flat directions, and it creates a huge baryonic number in homogeneities. Density in homogeneities is quite small at that period, but chemical inhomogeneities in chemical content is big, and only after QCD phase transition, then quarks become massless. There are bubbles of bubbles with very high baryonic number, roughly speaking, of stellar size. And at the moment, after QCD phase transition, this quarks turns into very massive proton or neutron, and huge density perturbation arise, and only after that they have formation of black holes. This is pictures of evolution, how this potential evolves. First it is no minimum, and then minimum disappears, and then it travels back, and so field started to move in this potential rotating. So probably have to more or less finish. There is the following picture. There are bubbles with large chi. Chi occupy a small fraction of the universe volume, but inside them there is very big baryonic number, and mostly they form black hole. It's possible to calculate mass distribution of those black holes, and it happens to agree with observation. Those baryonic bubbles who are not massive enough they would not form black holes, but they would form either primordial star or primordial antistars with quite funny properties. They would have unusual chemical content. They could look much older than normal stars. There is one star even observed which has lifetime bigger than the universe age. And this is easy to understand because its chemical content shows that it lived much, much longer than the universe. Not much, by 10 standard deviations. So there's another picture is not interesting. So outcome, as I already said, that there is PBH with log normal mass spectrum, that there could be compact stellar light objects, which would be quite unusual, and the strange star with unusual chemistry and very high velocity. They observed now. So I think there are some other ideas making dark matter of antimatter, and then another competing hypothesis that antistars can come from mirror neutron transformation to neutron. It's more complicated in my mind, but it's not excluded. Okay, so I think that there are this scenario that all black holes in the universe are primordial nicely solve the problem with too large amount of intermediate and supermassive black holes in not only in the present universe, but also in the very early one. Well, and there is, I would say, I can stop here so that not to be in conflict with organizers.
Thank you very much for finishing just in time, and thanks a lot for your talk. Are there any questions? Yeah, maybe Kazunori, you can go first.
Mm-hmm. Hi, Sasha. Thank you very much for interesting. Hello.
Nice to see you.
Yeah, nice to see you. Yes. Yeah, long time no see. Yeah, but yeah, actually, yeah, okay, very small point. But okay, pulsar cannot produce antiproton, but the supernova remnant can produce both of positron and antiproton through the PP collision, proton-proton collision. So what do you think about it?
Oh, say it again. Sometimes sound disappears. You're speaking about molecules or what?
No. Supernova remnants, not the pulsars. Supernova remnants can accelerate protons.
You're right, there could be, because a large amount of these primordial stars or antistars, they are indeed compacted. They are possible to be in our model, but in supernova remnants, I don't understand. That is usually in standard, in canonical scenario, they're simply normal star. They compact, but they could have large velocities, of course, but there are some of them maybe are going in direction of to galaxy. This our stars, the so-called our stars, behave like dark matter, and they're everywhere, moving with typical velocity of dark matter. And some of them can move towards galaxy. As supernova remnants, they moved out of galaxy, if I properly understood your question.
No. Inside the supernova remnant, the proton can be accelerated as a cosmic ray, right? And the proton-proton collision can produce both positrons and antiprotons. So
I see.
The antiprotons can be astrophysically produced.
Oh, I see. That's possible, but honestly speaking, we didn't study this possibility, but at least the flux of antiprotons, maybe. So, well, the answer is maybe it is relevant, and I don't know if speaking the answer. It's an interesting possibility. Thank you.
Yeah. Thank you very much.
All right, then Misha, please.
Hi, Sasha. A question. This log normal distribution for primordial black holes, from where it was derived? So
You see, I cannot say it in a simple way, but what happens? There is initially, but at some stage, the potential when phi is close to phi1 becomes started to have minimum, not in the origin, but some place away from that. And chi lives near the maximum of this potential. And then chi started to diffuse due to quantum fluctuations. And what we did, we used Sarabinsky diffusion equation and try and solve this, and found that it is indeed log normal. And then sometime later, some people working in solid state physics said that is usual situation if you have some kind of stochastic process with Brown motion. That's quite often they have log normal distribution. That's all what I can say. I don't have simple explanation. It was a big surprise to us that it happened to be so simple.
But this is for some particular model of inflation. Yeah, I'm asking because
no, model of inflation is we can have any model of inflation. We can have, and this for motion of practically massless field with flat potential. It is, you know, well-known instability of massless scalar field at de Sitter stage, and you know phi squared rises like m cube over time, or m to the force divided by the Hubble parameter force divided by m squared after all. And this is essentially this equation, which was this is diffusion equation which we solved and found that it is quite simple in this particular shape of the potential.
And
I'm sorry, Mish, I will think.
Okay, I will.
Maybe I find better answer.
Yeah. Well, another question is about second part of your talk. So when you said that anti-helium 4 atoms were found, you referred to talk of 2018, and so I wonder whether these results were published or if they were not.
Yes, it is published. It is. It was by some reason published very slowly. We have very strong reaction by the referee, and this was not just this is garbage, forget it, but good questions were asked. So preprint was in 2009 and publication was March 22. You see here.
No. I was asking.
Were in how to say it, in correspondence with the referee and asking indeed reasonable questions.
I see. No, but I was asking actually about Tink talks. You said that Tink gave a talk in 2018.
Yes. It was colloquium in Gran Sasso, November last year, and I was at this colloquium distantly, of course, and unfortunately I didn't copy anything. I should probably. Well, and talk was I'm more or less close to the how to say it, to what Tink have said, and I also we had some discussion with him, for example, that low energy anti-helium could escape observation, and he very low energy, and he gave long detailed answer and said no, we would not it would not escape observation. But Bonder, who is great detector man, said of course he would never see these objects. But anyhow, during our discussion, he said also that they would surely obtain, would see anti-silicon. So it was a kind of private discussion, private, that every participant of the workshop, of the seminar saw it. So it's, I don't know why that there are no publications of all observations of anti-helium by their work, but it is, people see it and refer to some seminars.
We'll see. Okay. Yeah,
Okay.
thank you
Probably.
very much. Thank you.
Okay, thank you too.
All right. Are there any more questions? If not, then let's thank Sasha again for the very nice talk and the discussions.
Okay.
And then if you could stop sharing, that would be amazing.
It's not amazing, but I think it would be fine. Okay. Okay. I stopped it. Correct?
Yeah, all good. Yeah, thanks a lot. And so the last speaker of the workshop will be Alex Kusenko, and I think he just appeared. So that would be great. All right.
Thank you. Yes.
Hi.
Yeah.
So maybe you can start sharing.
Okay, thank you. I'm sorry about my voice. Somehow I got sick with something that's not COVID. I actually tested negative this morning, but I was wiped out with fever all day. So apparently there are viruses out there.
Well, wait till tomorrow. The test may change then. Like.
Oh yeah, that's right. Yeah, I should test again tomorrow. Yes. So I'm sorry for missing the earlier talks, and I'm also sorry about the frog in my throat. So let me start sharing the screen.
All right. Yeah.
So
yeah, then yeah, seems all good. So our last speaker today is Alex Kusenko, and the last speaker of the conference, and he will talk about another talk about primordial black holes as dark matter and probably some other formation mechanisms. So please, Alex, the floor is yours.
Yeah, thank you very much. So indeed, I will describe some new formation mechanisms that may not have been discussed earlier. And once again, I apologize for missing the earlier talks. My main motivation for discussing black holes as dark matter comes from the fact that black holes actually exist in nature. Of all dark matter candidates, it's the only one that is known to exist. That doesn't mean that new physics is not playing a role in producing some population of black holes. However, this is very encouraging to know that this object is part of nature, and it was discovered by astronomers in our galaxy. And in 2020, Roger Penrose, a theorist, and two astronomers, Gensel and Guess, got a Nobel Prize for discovering supermassive black hole in our galaxy. And when I give talks at UCLA, I make a joke that Sagittarius A star stands for the name of the constellation. A stands for Andrea, and stars stand for the stars that she used to discover it, because it's the trajectory of these stars that were essential in pinpointing a very strong gravitational attraction source. So dark matter can be made entirely of black holes in this window between 10 to the minus 17 and 10 to the minus 11 solar masses, where the black holes can make up to 100% of dark matter. All the rest of the mass range is closed by various constraints, and we can discuss those constraints if you want. And there is even a set of candidate events already, which can be interpreted as primordial black holes. There was a recent search by HyperSupremeCam, HSC, an instrument on Subaru telescope, which allows you to take snapshots of Andromeda galaxy, with a frequency of once per 2 minutes, and see if one of the stars would get amplified by a black hole passing through the line of sight. So this star here could indeed have been magnified by a black hole. And if that's the case, this black hole has a mass between 10 to the minus 9 and 10 to the minus 5, and this purple, this pinkish region is the mass range for this event. Earlier search by Ogli also turned up 2 dark matter candidates, and their masses would be in this range. Okay, so the question is, can we explore some formation scenarios that lead to a dark matter population of black holes? And I will try to add to the existing cookbook of primordial black hole formation. So this is simple recipes for making black holes. Each of them takes about 30 minutes or less. That's the time available in the early universe. And the horizon size on your screen is the size of the universe horizon at the time of electroweak phase transition, for example, just to set the scale. And this also is drawn to scale. If you squeeze this horizon by about 13%, you get a black hole. So that is the idea of the most explored avenue for making black holes, and that is making black holes by having some inflationary perturbation come into the horizon and causing it to collapse to a black hole. What I'm going to explore is some other scenarios that actually work on sub-horizon scales, and they make multiple smaller black holes smaller than the horizon size at the time of formation. And one very simple example that leads to it is a system that has just Yukawa interactions mediated by long-range, mediated by scalar forces among some heavy fermions. Right? So interactions like this can create an attractive potential, which is y squared over r, and it's just the same potential that as Newton's gravitational attraction potential. So just as the structures can form because of gravitational instability, here we have a new attractive force. And when the universe is small enough, when the Hubble size is small enough to fit within the Compton wavelengths of this scalar particle, then this new attractive force can also mediate an attraction, and it will exhibit the same gravitational instability. Okay, so this leads to formation of structure, and we can see this by examining a uniform solution, even in radiation-dominated era. And so little delta here is the total energy density, and big delta counts the number of fermions. And so this quantity does not grow in radiation-dominated era, as we all know. However, this quantity, the overdensities of particles interacting by a Yukawa force, can grow independently and create these isocurvature perturbations, which are essentially halos of these particles, right? You can see that the solution you obtain grows very fast when the Yukawa coupling is significantly, when the Yukawa force is significantly stronger than gravity. This is verified in this preliminary work by Derek Inman, who does n-body simulations for this attractive force and observes that indeed you start with a homogeneous distribution of particles and you end up with these clumps of particles. And this happens in radiation-dominated era, right? So you don't need to wait until matter-dominated era. Okay, so then, okay, you form some structures, you form some little halos of dark matter particles in the early universe, and nothing happens to them, right? I mean, our galaxy is not going into a black hole anytime soon. However, the very same interaction that we just introduced, the Yukawa interaction, also opens up a channel for radiative cooling. And these halos can radiate from Bremsstrahlung, from these particles colliding with each other, until so you take the energy out of the halo, and the halo gets smaller and smaller, and eventually finds itself inside its own Schwarzschild radius. So this formation mechanism produces a mass function, which is probably, to some approximation, can be described by a Press-Schechter formalism, because you have little halos, they merge, the attractive, two-body forces are the same as Newton's law. So if you apply Press-Schechter formalism, you will get a mass function like this, and can fit in this window, explaining all of the dark matter. Now, if you don't want to worry about the annihilation of these particles, then you also can consider some asymmetry, right? There are many models of asymmetric dark matter where the asymmetry in the dark sector is the same as in visible sector. And then you use the same trick as people use in the case of asymmetric dark matter to explain the dark matter to ordinary matter ratio. In fact, you get just the right amount for the baryon, for the asymmetry equal the baryon asymmetry, and for the electroweak mass particle. Okay, so this is one scenario, and feel free to interrupt me, please, if so. I told you something very unusual already, right? I told you that structures can grow in the middle of radiation-dominated era, and that they can radiate energy and collapse to black holes, right? So this is this first scenario I wanted to add to existing cookbook. Next, let me consider supersymmetry. I will just consider MSSM without any additional elements, right? So I'm not inventing a model. I'm taking a model from the shelf and working it out. Okay, so this any model with supersymmetry has flat directions that can develop large expectations values in the early universe, and that is the essence of Affleck-Dine baryogenesis. After that, the flat direction has to come down to the origin, and as it does so, it develops an instability. So that flat direction can start homogeneous in space, but it doesn't remain homogeneous in space. It breaks up into lumps. And one way to think about this is to observe that self-interaction in the flat direction has, in the Tyler series expansion, the terms that go as cubic, and they mediate attractive forces. And just as Yukawa force, these attractive forces cause an instability. And so this attractive instability, again, is much stronger than gravity and causes this to collapse. Misha Shaposhnikov and I used a different approach to describe these instabilities. We applied small perturbations to a homogeneous solution and observed these perturbations grow exponentially. The same problem was analyzed numerically, and so it's a very well understood instability in the evolution of the scalar condensate. And the result is that you have a substance in the universe which is just like matter, except it's made of very few very heavy particles, right? It's a, normally you have zillion of particles in the matter dominated universe, but and the fluctuations are small, they're suppressed by 1 over the square root of the number of particles. But Poisson fluctuations become large when the number of particles is small. And if this fragmentation happens before radiation-dominated universe or in the beginning, this population of lumps or cuboles can overtake the total energy density, come to dominate over the universe, and then decay, leaving behind nothing except for some configurations that can collapse to black holes. Now, those are very few, because in order for the configuration to collapse to a black hole, it has to be an overdensity, and it has to have very small angular momentum. So in other words, the velocities of the particles should all point to the center of mass, okay? But very rarely, sometimes, you will find such configurations. And with all the penalties taken into account, we count the probabilities of this happening. And of course, the energy density is tiny compared to the overall energy density in the universe. But because you do it very early on, you only need a tiny density of dark matter particles. So these black holes cannot be undone once they formed, and they just exist and eventually come to dominate and become dark matter. So I was just visiting Paris, and I made this joke about Poisson fluctuations, because Poisson in French means was fish, and I showed the picture of many. When you have many particles, the fluctuations are small, and this is the picture of the Poisson I took on Focarava. But when the system is dominated by few giant particles, then the fluctuations become large, illustrated by this picture taken on the island of Rangiroa, when some dolphins came and let my wife touch and pet them. And of course, you can always wonder whether Poisson is the right distribution here. And the answer is I don't know. And in fact, dolphins are not fish. So, this is not a true Poisson fluctuation, but it sure looks like one. So with this picture in mind, I can now calculate the population of black holes produced from Affleck-Dine baryogenesis, essentially. And the overall height of this curve, the abundance, is model dependent. However, the mass scale is fixed by some fundamental parameters such as M-Planck and the supersymmetry breaking scale. And it turns out to be right in the range where all dark matter can exist in the form of primordial black holes. So that's interesting. Another recipe. Again, I will take supersymmetry. Again, I will just take MSSM, but the scenario will be very different, and the mass function will be very different. Now, in addition to cuboles that form from the field phi, I will allow another flat direction coupled to phi through the scalar potential to exist and to have a much smaller mass than the mass of the field phi. In this case, the attractive forces, so it's sort of a combination of the Yukawa interaction and of the previous scenario. Now we're making the black hole out of cuboles, but the cuboles have attractive forces. And now the baryonic charge in cuboles is pulled into one giant cubole, and that cubole grows until it reaches the point where it collapses to black hole. Okay, so that sets a characteristic mass at which the collapse occurs, and so the mass function now is delta function. But again, it's in the same mass range because this mass range knows about Planck mass and supersymmetry breaking scale. There was another scenario that I think should be mentioned. So this was invented by Deng and Vilenkin, and they use a slightly different form of the inflaton potential. We only modified the shape of the inflaton potential a bit. They describe this phenomenon very well. And so if you have an inflaton rolling in this Mexican hat, and the Mexican hat has a dip in the middle, then sometimes the inflaton can tunnel into that dip and create a bubble. If that bubble is big enough, it becomes an independent baby universe and expands for the internal observer, but to the external observer, it looks like a black hole. If that bubble is small, then it recollapses, but to the external observer, it looks like a overdensity of energy, which then collapses and makes a black hole. And what is interesting in this Vilenkin scenario is that the mass function has a characteristic 1 over square root of m tail, and with these HSC observations, which my colleagues in Japan and I now have more time for observing on Subaru, we hope to push it down. And so even though we can't push it to the left, we can push it down and hopefully catch this distribution by the tail, by this 1 over square root of mass tail. All these different scenarios have different predictions for the spin. And if future observations can tell us the spins of black holes, we may have a new window on the early universe, because from the spins we can learn that, first we need to discover primordial black holes, but then from the spins we can learn what mechanism led to their formation. And I want to mention one more interesting effect that primordial black holes could have on today's universe, and that is the destruction of neutron stars. If a small black hole gets inside a neutron star, then it consumes it from the inside and eventually causes it to become a black hole, right? So there's this channel for systematic destruction of the neutron stars, also known as neutron star genocide. So these black holes are, the primordial black holes can have any mass function at all, but after processing a neutron star, they all become 1 to 2 solar mass black holes because that's the neutron star masses. And that is a good way to observe them. Also, in the last stages of collapse, this rapidly spinning neutron star can release enough neutron-rich material to explain our process nucleosynthesis. I will skip a few slides just for the sake of not running out of time, but if you have primordial black holes that compose more than a few percent of dark matter, you can explain all or part of our process nucleosynthesis, which is the synthesis of elements heavier than iron. And that can be an additional contribution in addition to neutron star collision. So ask me in the question session and I can tell you more about that. The population of 1 to 2 solar mass black holes would be very unusual and would be a smoking gun for primordial black holes because astrophysical processes are not good for making these black holes. So if future gravitational wave observations discover such a population, that can tell us that primordial black holes exist. Okay, and I will stop with this conclusion slide and take questions. Thank you.
So thanks a lot for a very nice talk. So you even finished a bit ahead of time, but yeah, more time for questions. So are there any questions? So, Inar?
Yes, so maybe to this slides which you, yeah, so thank you very much for the nice talk, first of all. So maybe going back to those slides which you skipped about our processes, but
yes.
Can you maybe comment on the status? So is this still an issue, like producing heavy elements, or what's the current?
Right. So to produce, so you know that elements up to lithium are made in the Big Bang, but then all the heavier elements have to be made in stellar evolution. So they have to be made in stellar burning and also in supernova explosions. And that explains very well the abundances of elements up to iron. Now, past iron, the abundances look like this curve with these big peaks at gold, platinum, uranium, at all the important elements. And it would be, you wouldn't be able to explain this if you started adding neutrons one by one to iron, because then you would end up with a decreasing function, not a function that has peaks. However, if you start with neutron-rich material, then neutrons stick together and drive the system towards these islands of stability, creating these peaks. So that shape can actually be explained very well. So if you look at this neutron number, proton number diagram, this is the value of stability for nuclei. And if you go in the direction of more numerous neutrons, then the nuclei become unstable. But if you have substantial volume filled with high neutron density material, then the system will start from here and evolve towards these big peaks. Okay, so what you need is to find a place where neutron-rich material is released. And one very good place for that is neutron star mergers. We have observed one of them. It was triggered by observations of gravitational waves by LIGO. And then the astronomers turned their telescopes and looked in the spot, and they observed what is known as a kilonova. And that is the optical counterpart of this neutron-rich material decaying, heating up, and producing light in addition to heavy elements. Now, if you just try to model this with a single zone production, if light you see comes from the same place where these heavy elements are made, you're not going to explain the observation, right? Because you'll get this red curve, and and the data points are all too blue to agree with that curve. However, if you assume there are several zones, maybe you're seeing a different part of the kilonova from the part where the heavy elements are made, then you can fit the data, and everything works. However, then you still haven't seen the proof that the elements are made there, right? Because you're assuming that there are different zones, several zones that produce this light. And sorry. And some astronomers believe that this scenario is not explaining quantitatively the observed, the needed number of our process-enriched material. Here's a headline: "Scientists dazed and confused by extraordinary amount of gold in the universe," which stands for the fact that some people show that there's not enough material you produce in neutron star collisions. Another piece of observation is that the distribution of our process material is non-uniform. So one dwarf galaxy, Reticulum 2, shows a huge enhancement in terms of heavy elements, and the rest of them show nothing, right? So the distribution of gold among galaxies is the same as the distribution of gold among people. One has everything, the rest have nothing, okay? And that points to a rare event, right? So if there is a neutron star eaten by a black hole, that would be a rare event. And the number densities work out, right? So, sorry, not number, the frequency works out. So this is one way that black holes can contribute. We don't know how much they contribute. We don't know how much they should contribute. But the fact that there are no pulsars in the galactic center or in any of the dense environments with dark matter is suggestive, right? So people used to think that the paucity of neutron stars in the galactic center could be explained by obscuration by interstellar medium absorbing radio waves. But now a very young magnetar was discovered in the center, and now we know the optical depth, and it's not nearly big enough to obscure the signals of radio pulsars. So there is a problem with that. How are we going to know if this is happening? Well, you need to observe. So when a neutron star is destroyed by a black hole, the deviations from axial symmetry are not very big. Certainly not as big when you have two neutron stars spinning around. So the quadrupole moment is not so big. And so then the gravitational wave signal is very weak, and also it doesn't have the characteristic chirp of two neutron stars coming together and making a black hole. So what you need is to observe a kilonova event, the optical signature of this event, without a gravitational wave counterpart. So the gravitational waves usually used as a trigger for astronomical observations, and we've never observed a kilonova without knowing where to look. But future surveys, including Rubin's survey, can discover several such kilonova per year, and that would be a smoking gun for primordial black holes. Another interesting thing is that the neutron-rich material released in this fashion also generates a population of positrons, which within huge uncertainties can be consistent with what is needed to explain the observed 511 keV line from the galactic center. But the uncertainties are huge. And yet another observation of this neutron star genocide is that you should observe some fast radio bursts coming from this process. Now, fast radio bursts are radio bursts on the time of the milliseconds, And here you have a huge magnet, a neutron star, which in the last milliseconds of its demise is being massaged into something else. It's being squeezed into a black hole. So you take a magnetic field, you make it time dependent on millisecond timescales, you're going to produce radio waves, and that burst comes, on the millisecond timescale. Okay. So that is the set of slides that I initially skipped. Thank you very much for bringing it up.
Yeah, thank you very much.
Yeah, thanks a lot for the second half of the talk. So if there are no other questions, let me maybe ask. So you briefly alluded to it already, but can you elaborate on the observational evidence for the lack of neutron stars? So
Right. So this is very interesting. So neutron stars are seen as pulsars, and most of them are seen nearby just because they're loudest, right? So there's 700 pulsars within one kiloparsec of Earth, right? Within 1 kiloparsec of the solar system. But we do have observations of neutron stars, from more distant objects, and now we do have very sensitive radio telescopes. So we should have seen something coming out of the galactic center, and yet, there's nothing. And this goes by the name of missing pulsar problem. And in the past, people argued that maybe interstellar medium is opaque enough to radio waves, so we wouldn't see those radio waves from the galactic center. The galactic center is where most of the stars are, and that's where most of the neutron stars should be born. So that would be the place to look. But recently, a magnetar was discovered right next to the center of the galaxy, very close to Sagittarius A star. And that magnetar is very young, so it would not have been affected by black holes yet. But the signals from that magnetar come on, tell us the optical depths of the interstellar medium, and it turns out that we should have seen the pulsars there. So an optimist can take this as a hint that maybe pulsars are destroyed by neutron stars, and maybe dark matter is primordial black holes. Then you might also ask, okay, what about other places where neutron stars would be destroyed by black holes? Well, centers of dwarf galaxies have a lot of dark matter, and they don't have, there's not a single neutron star known to be hosted by any of the dwarf galaxies. And again, an optimist can take this as a hint of detection. But that's basically it, right? Now, there are many neutron stars in globular clusters, and some people tried to hypothesize that maybe globular clusters carry a big overdensity of dark matter, and they even tried to use that as a source of constraints on PBH. But globular clusters have so many stars that people have studied the kinematics of stars over the years and were able to map the gravitational potential of globular clusters. So just from velocity dispersion, we know that these systems do not contain dark matter. So the dark matter inside the globular cluster can only be factor 1.5 or 2 denser than the dark matter outside the globular cluster. And these clusters form not because they have anything to do with dark matter, but because there was a giant molecular cloud that produced a lot of stars. Now, there was some confusion early on, many years ago, before people understood this, because the mass of the globular cluster is something like 10 to the 6 solar masses, and it's coincident with the masses of the first halos that collapsed early in the history of the universe. But that is purely a coincidence, and the globular clusters do not host large amounts of dark matter. So there, the neutron stars are safe. But any other place where dark matter is abundant appears to have no neutron stars.
And so just to make sure I understand correctly, really zero. So it's not that there's a few or something, really zero detected in the high dark matter environment.
Right.
Okay, cool. Yeah, there's a question by Valerie.
Yeah, concerning going back to center of galaxies and lack of neutron stars there. Do the numbers work out right in that case?
Yes, yes. So the numbers are model dependent somewhat, but because the smaller is the PBH mass, the higher is the number density, and also the dark matter profile has significant uncertainties, right? So in the center, but the numbers do work out that you can get, for example, with respect to our process nucleosynthesis, what you need in the history of our galaxy is to produce 10 to the 4 solar mass of 10 to 4 solar masses of our process enriched material the high density neutron rich material. And so that means that you would need 10 to the 5, 10 to the 6 neutron stars to be destroyed, because each of them produces a few percent of that. And that is consistent with the rates you expect from neutron stars capturing the black holes. Once the neutron star captures the black hole, its fate is sealed and is going to be destroyed. Right? So it's just the capture rate that matters. And the capture rate is also not so easy to calculate, and there was some debate among people what the capture rate is, but I think it's pretty much settled. So with all these estimates and within astrophysical uncertainties, the numbers do work out.
All right. So if this answers the question, then so Valerie, you muted.
Yes, I forgot to lower my hand.
All right. Then Kazunori, please.
Yes, Alex, hi. I already discussed this problem of the redistribution of neutron stars on Slack with you and Hitoshi Murayama. What about the pulsar kick? And if they have a large velocity dispersion, then automatically the population can be redistributed, and they may left the disk region, and they may live in halo region. What about this interpretation?
Yeah, so the population studies have not helped explain the missing pulsar problem. Now, most of the pulsars have velocity dispersions. So a typical velocity of a pulsar is something like 400 kilometers per second, right?
Right.
So
very big, yes.
Right. So now there are some. In fact, there's 15% of the pulsars that have velocities greater than 1,000 kilometers per second, and those are not even bound to our galaxy. They are leaving. They will leave the gravitational potential. But there's also But there's also a population of neutron stars that have lower velocity, and many neutron stars are born in binary systems, in which case that velocity kick is distributed between the two stars. A supernova explosion typically does not disrupt a binary system. So if you have two stars, one of them going through supernova, the resulting neutron star will still be part of the binary. And then when the second star goes through supernova, you'll get a binary pulsar, right? So in that case, the first kick was wasted on the mass of the big star that was attached to that pulsar, right? So there's there is a substantial population of neutron stars that have fairly low velocities, and people looked into that in connection with the missing pulsar problem, and they have not been able to explain it. Now, if these analyses are wrong, then that would be very interesting to then you should publish and point this out. You should actually look at what the population is expected to be, and if you can clear up the galactic bulge of any pulsars through kicks, that would be interesting. But I don't think that is going to happen, just because there are so many neutron stars with low velocities.
Right. Yeah. Actually, there is a counter argument to produce neutron star binaries, because if just a mass if progenitor star lost most of the mass without kicking, then binary is disrupted, right? Destroyed. But if they have a kick velocity, then statistically some fraction of neutron star could be again produce the binary. So it's a good counter argument. Actually, due to a high velocity, it may keep a binary. Do you agree with it?
Yeah, so I mean, there are actually many dynamical effects here that come into play.
Right.
So I think
Right.
that it would be good to look into this and you know, and sort them out and write a paper. What is the expected population of radio pulsars in the galactic center? And I think that people have tried to attempt this, but maybe they, you know, maybe there is a way to do a better job.
Okay. Yeah, interesting. Yeah. Thank you very much.
Thank you. Thank you.
All right. So if there are no more questions, then let's thank Alex again for the very nice talk and discussions. And then we conclude our conference. So thanks a lot to all the speakers for their contributions. Thanks a lot to all the participants for the very active discussions. And we will leave the Zoom room open for a few more minutes. So if you still want to have some more informal discussion, then feel free to stay. And otherwise, thanks a lot for participating and have a nice weekend.
Yeah, thank you.
Thank you. Thank you.
Thank the organizers for organizing this nice workshop. And that was certainly a lot of work, but it was very useful. Thank you very much, guys.
Thank you.
Yeah, thanks a lot for coming.
Bye. Sorry, I don't know if you hear me. I just want to comment something. I don't know if anyone here is interested in the problem of time or time as the